Hello everyone. So this is going to be the second part in our 2D vectors from head to tail comprehensive review. So today we're going to be adding vectors at different angles. So in this one we've finally thrown out our beautiful right triangles and now we've got to work with really gross individual vectors instead. So you'll find that getting numerical values for the resultant is a little bit less easy in this case. And so we're going to split these vectors into x and y axis components in order to make it possible to add them together as we would normally. So in order to do that, we're going to start with our first vector here. And so what we've got is a soccer ball that's been kicked by one player to a velocity of 5 meters per second at maybe 50 degrees from this reference point, which we'll call the x-axis. So let's go ahead and draw this one out. So if we have this vector here, 5 meters per second, then our components are going to be in the x and y direction. So we'll have an x component here along the x-axis, and we'll have a y component here along the y-axis. So we'll call this k1x, and we'll call this one k1y. And our angle is 50 degrees. So if you use our Pythagorean theorem at this point, then you should remember that the sine of an angle is going to be the opposite over the hypotenuse, and the cosine of an angle is going to be the adjacent over the hypotenuse. So if we use that logic, then we come up with these two equations here, where the x component in general is going to correspond to the cosine of the angle, and the y component is going to generally correspond to the sine of the angle. This only applies if you measure your angle from the x-axis. So always be careful and make sure that you're checking your trig functions just to make sure that they're being used for the right components. So in this case, k1x is going to be equal to k1 times cosine of theta, which is equal to 5 times cosine of 50, which, if you put that into your calculators, go ahead and pause and get the number, and then we'll convene. All right, so the number that we've got here is 3.214, let's say, meters per second. Now our y component is going to be k1y equals k1 times sine of theta, which is equal to 5 times sine of 50. Which, go ahead and pause, put that in your calculator. And we get 3.83 meters per second. All right, so we've got the components for K1. So now let's look at Kik2 and what that's done here. So I'll have you go through this one on your own, and so if you want to do that, you can go ahead and pause, and then I'm going to work through this one a little bit faster. So we're going to start with this vector down here, and this is our horizontal component. And I like to measure the angle from the x-axis, just so the conventions are always the same. So this is 7 meters per second. So if we're solving for k2 of x, that's going to be 7 times cosine, because it's x, of 50. And k2 of y is going to be 7 times sine of 50. Or, oh, sorry, not 50. 10. My apologies. And the angle is 10. So in this case, we get a value of negative, okay, so here's something. So if you consider the negative part of the x-axis, if the ball is the origin, then this angle is really 10 plus 180 degrees, because we always rotate our angles around from the positive x-axis. So you could do this in two ways. You can either calculate the angle, or you can calculate the value according to 10 degrees, and then assess the sine of that value after the fact. Like, we know that because this is going to be down and then to the left, both of those values are going to be negative. Another option is you can take this 10 degrees and add it to 180, and then if you plug cosine of 190 or sine of 190 into your calculator, it will adopt the proper sign for this vector. So either way, you should expect to get negative 6.894, let's say, meters per second. And for the y component, you will get negative 1.22 meters per second. So now we have our components, and now they're nice and beautiful, and we can add them up. So let's go ahead and do that. So let's say if we want the resultant, r sub x, that's going to be equal to 3.214 plus, and this is a negative, so it's going to be negative 6.894 meters per second. So if you plug that in, you end up getting negative 3.68 meters per second. And if you do r sub y, you add 3.83 plus negative 1.22. And what you get from that is positive 2.615 meters per second. So these define our resultant vector. So we have now officially gotten a vector, and not only that, but we've gotten our resultant vector in terms of x and y components. So if we were to sketch this out, we would say maybe it's going to be go up by 2 in the y direction and then negative 3 in the x direction. So you could expect maybe our vector looks something like this. It's a little shorter than the other two, but that's just how things add up. So if we want to find the actual magnitude of this resultant, then you would go ahead and use our Pythagorean theorem. So that would just be square root of rx squared plus ry squared. And if we wanted to find the angle of our vector, we would say the angle is the tangent inverse of the opposite side over the adjacent side. So that's going to be ry over rx. Now, because we've done this in a previous part or a previous video, if you're not sure how to go about this part, go ahead and refer to that video. And I would say the only other thing to note here is that you need to take the direction into account when you're calculating the angle. Because if you simply, my advice would be to go ahead and make both of the values that you plug in here positive. So you just get the raw angle. And then looking at this, we know that the angle has to be it has to be rotated up from the x-axis by that amount. And so in this case, you would say if you have an angle, maybe let's say this angle here is let's say like 60 degrees. Then you would say that your angle is going to be 180 minus 60 degrees. And so then your final angle from here to here would be 120 degrees from the x-axis. So that is not the correct number for this, but you can apply, go ahead and do the calculations for this and apply that logic to it. And that is generally how you can tackle any of these problems here. So thank you for watching. I hope this helped, and I wish you luck on your endeavors with 2D vectors.